Hello everyone and welcome to Physicmania. In today's video we're going to see the vector product, also known as the cross product. If you want to go to specific parts of this video, please go to the box description where you will have the times of the video. So without further ado, let's start. The cross product, also known as the vector product, is simply the product of two vectors that has as a result another vector. The notation we use for this multiplication is the vector A, a vector A given, multiply, where we say the multiplication symbol is an X, times the vector B being equals to this new vector called C. And also we say that the magnitude of this vector C is equal to the magnitude of vector A times the magnitude of vector B times the sine of the angle between the two vectors A and B, as we can see in this picture here. Now, the resultant vector C is given in the perpendicular direction to both vector B and vector A. This means that vector C makes a 90-degree angle with vector A and also makes a 90-degree angle with vector B. An interesting property of the cross product is that because the vector A and the vector B can be expanded to create a two-dimensional plane, when we take the cross product of these two vectors and we generate a resultant vector which we're calling C, this vector actually can be in the upward direction or in the downward direction, since we are now in a three-dimensional plane and the direction perpendicular to both B and A can be given in the upward direction or in the downward direction. So how do we know what is the positive direction or the negative direction of the cross product? Well, this is given by the notation that we're using and something called the right-hand rule, as can be seen here. So if we have that the cross product between vector A and vector B is given in this way, what this is telling us is that using the right-hand rule, we should point our index finger, as we can see in this picture, in the direction of vector A, and then we should point the middle finger in the direction of B, and then we should extend our thumb finger in the upward direction as much as we can, and this will give us the positive direction. So in this case, A cross B is equal to C in the upward direction. But what happens if we had B cross or the cross product with vector A? Then we should point the index finger in the direction of B and the middle finger in the direction of vector A, and this will result in our thumb finger pointing in the downward direction. Then this means that our resultant vector C is opposite to the previous cross product that we made. Therefore, we have that A cross with vector B is opposite or is negative to the vector created with the cross product between vector B and vector A. This is the asymmetry of the cross product. Now let's see how to find the cross product in terms of components. To do this, we're going to be using the unit vectors as last time with the dot product. So let's pick first the same unit vector, for example, the x unit vector. If we make the cross product with itself, we have the magnitude of the unit vector x times the magnitude of the unit vector x times the sine of 0, since the angle between the unit vector with itself is 0. This gives us a result equals to 0. Then for the other unit vectors with itself, let's say the unit vector y and the unit vector c, we have the same result. The cross product with itself is equal to 0. Then what happens if we take the cross product of the unit vector x with the unit vector y? Then we have, from this formula that we found before, that we have the magnitude of the unit vector x times the magnitude of the unit vector y times the sine of the angle between them, and the angle between them is 90 degrees, and we know that the sine of 90 degrees is equal to 1. And now we have to also find what is the direction of this unit vector n, and this unit vector n, the only thing that it represents is the direction that is perpendicular to both the x-axis and the y-axis. Therefore, now using the right-hand rule, if we have x, y, and z, right, and we point the index finger in the x direction and the middle finger in the direction of y, then our thumb points in the direction of z. Therefore, our result is that the magnitude of these both unit vectors is 1, so it's 1 times 1, and sine of 90 is 1, so times 1, times the direction in which this cross product gives us by the right hand rule, which is c. Therefore, the cross product of x times y is equal to the c component. Now, if we do the cross product of the unit vector y times the unit vector c, we have the magnitude of y times the magnitude of c times sine of 90 degrees, and using the right hand rule, again, we see that the direction is in the x-axis, so this gives us that the cross product of y times c is the unit vector x. Then for the unit vector c times the unit vector x, we have c times x, the magnitude of both of these vectors, times the sine of 90 degrees again, and then using the right hand rule, we see that the direction is the unit vector y, which again gives us that the cross product of c times x is equal to the unit vector y. Then, so what happens if we take these cross products of the unit vectors in the opposite way, meaning y times x instead of x times y? Then we have, as we have seen before, that the result is in the opposite direction to what we have to what we found. So we have that the result for this the cross product is the negative of the c unit vector, and the same for the other two cross products. C times y will be negative x, and x times c will be negative y. Now we are ready to make the cross product of two vectors using components. So let's say that we're given vector A and we make the cross product of vector A with vector B. So because we can write now the vector A in components, we have AX in the x direction plus AY in the y direction plus AC in the c direction, cross product with BX in the x direction plus BY in the y direction plus BC in the c direction. And distributing this out, we have AX times BX and the cross product of the unit vector x with itself, which we know gives 0, plus AX times BY times the cross product of x with y, which we know gives c, then plus AX times BC times the cross product of unit vector x times c, which gives negative y, plus AY times BX times the cross product of y with x, which gives negative c, plus AY times BY times the cross product of the unit vector y with itself, which again gives 0, plus AY times BC times the cross product of the unit vector y times c, which gives the unit vector x, plus AC times BX times the unit vector c times x, which gives the unit vector y, plus AC plus BY times the unit vector C cross product with Y, which gives negative X, and finally plus AC times BC times the cross product of C with itself, which gives 0. Then we have the result that in the X direction we have AY times BC minus AC times BY, plus in the Y direction we have AC times BX minus AX times BX, plus in the C direction AX times BY minus BX times AY. Therefore, the cross product of A times B in terms of components is in the X direction is AY times BC minus AC times BY, plus in the Y direction AC times BX minus AX times BC, plus in the C direction AX times BY minus BX. Since the cross product of A times B gives us another resultant vector called C, we can find the components of this vector using the equations that we found above. So for example, the component of vector B of vector C in the X coordinate is given from above AY times BC minus AC times BY. The Y component will be AC times BX minus AX times BC, and the C component will be AX times BY minus AY times. Now let's look at an example in which we're given a vector A and a vector B, in which vector A has a magnitude of 6 meters and lies in the X coordinates, and vector B lies in the XY plane and makes an angle of 30 degrees with respect to the X coordinate, and the magnitude of vector B is equal to 4 meters. Okay, so we can do this problem in two ways. We can use this formula that we found before, or we can use the components to find our result. So let's start with this formula, with the formula in which we use the magnitude and the direction. And the first thing we're going to do is find the magnitude of vector C. So we know that the magnitude of vector C is given by the magnitude of A times the magnitude of B times sine of the angle. So we have the magnitude is 6 meters times 4 meters times sine of 30, which this gives us 12 meters squared. Now, how do we find the direction of vector C? Simply, we can just use the right hand rule. So since using this notation, we have A cross B, so this means that the index finger must point in the direction of A, then the middle finger must point in the direction of B, and then we expand our thumb finger, which will point in the direction of the C unit vector. Therefore, our resultant vector C is equal to 12 meters in the C direction. Now we can use the components, and as we can see here, right, vector A only lies in the X coordinates, so we have that AX is equal to 6 meters, AY is equal to 0, and AC is equal to 0. Then we find the components of vector B, and as we can see, the vector B is making a right triangle, so we have Bx is equal to B times cosine of phi, which gives us 4 meters times cosine of 30, which is equal to 2 times the square root of 3. Then By is equal to B times sine of phi, which is equal to 4 meters times sine of 30 degrees, which is equal to 2 meters. And vector B does not have any components in the C direction, so BC is equal to 0. With the components found, now we can use the equations that we find above, and we have that the component of vector C in the X direction is AY times BC minus BY times AC, which is 0 times 0 minus 2 meters times 0, which is equal to 0. Then CY is equal to BX times AC minus AX times BC, which is equal to 2 times the square root of 3 times 0 minus 6 times 0 which is equal to 0. Then C in the C component of vector C is equal to AX times BY minus AY times BX, which is equal to 6 meters times 2 meters minus 0 times 2 times the square root of 3, which is equal to 12 meters. Therefore, our vector C has only components in the C direction, as we can see here, and our resultant vector C will be equals to 12 meters in the C direction.